Hello, I am Frank Gallagher from the NOAA NESDA's Office of System Architecture and Advanced Planning, and I'm happy to talk to you today about a new paradigm for NOAA low Earth orbit capabilities and architecture. But before I start, I'd like to mention my co-authors, Dave Spencer, who's the Chief Technologist in OSAP in our group, and Vanessa Griffin, who is the Director of OSAP. So NESDA's conducted the NOAA Satellite Observing System Architecture Study from about 2014 to 2018, where we looked at various architectures, over 150, close to 200 different architectures of space, the space mission, where we were trying to find the most cost-effective architecture for NOAA to use in the future time frame being after JPSS and GOES-R in the 2030s through the 2050s. NOAA is currently using the results today to start implementing some of the recommendations from the NSOSA study, and we'll talk about a few of those today. Even before the NSOSA study was completed, though, in 2018, we were already starting to see some strong signals that came out of that study, and one of the signals that we saw was that it was probably not in our best interest to build very large, very expensive satellites in the future, satellites that are launched irregularly and fairly distant from each other, where it's very, very difficult to bring in new technologies and new capabilities in that particular program. So one of the things that we saw out of that was disaggregating the LEO architecture, where we would put the high availability measurements on a particular platform and lower availability measurements on one or more other platforms, where we could launch them at different rates. 2 years ago, though, Congress also enacted a law that said, NOAA, you need to take a look at the results of the NSOSA study and start enacting them. And out of that law and out of that recommendation from the NSOSA study, we started to look a little bit more detailed about what the results meant and how we could start implementing them. So one of the things that came out that was a strong signal is that we wanted to have a mix of various types of measurements that are of high impact. And we want to make sure that they were they were flown on small platforms and medium-sized platforms, as I mentioned earlier. We don't really want to fly the really big platforms anymore. And we also want to make sure that we develop an architecture that has greater agility. Technology is changing very, very rapidly in both the instrument side, the satellite bus side, and launch side. And we want to make sure that NOAA is in a position to be able to take care of those changes. So we want to make sure that we have the ability to on-ramp new technologies as best that we can in order to meet more user needs, but also to be able to take advantage of smaller mass, better electronics, better communication capabilities, those kind of things. And we also wanted to make sure that we would have an opportunity to fly some of these things as an instrument of opportunity on some of our missions. So, why are we doing this now? Why do we need to take a look at this? We just launched JPSS-1 not too long ago, and it's operating beautifully in orbit. So why do we need to look to the future so soon? Well, if you look at this flyout chart, one of the things that you can see is NOAA 15, NOAA 18, NOAA 19, our older type systems, which still produce valuable soundings, are well beyond their lifetime. Because they're producing valuable soundings, data and other types of data, in orbits that are different from where we're flying JPSS or where we're using our European partner data, it gives us a diversity of measurements that really help out numerical weather prediction, NWP. In addition, our partners in the U.S. Air Force flying the Defense Meteorological Satellite Program satellites are also reaching the end of their life, and they fly in the early morning orbit, which even adds more to diversity of our measurements. And we want to make sure that we can try and maintain that diversity as we go along. JPSS-2, JPSS-3, and so on are all going to fly in the same orbit in the early afternoon, and we want to make sure that we don't lose this orbital diversity or have this data loss. So maintaining a diverse portfolio of orbits and of measurements is very important to numerical weather prediction and hence our customers. So small satellites offer probably the greatest opportunity, an opportunity we really haven't seen before, for NOAA to move quickly to bring these new technologies into orbit sooner and at a reduced cost for the American taxpayer. So we have this opportunity to create this new agile, adaptable constellation. Those are keywords that I'm going to be using over and over again, because that's something that we really see as an opportunity in NOAA to help our mission. And there's a number of capabilities that we're considering. I already mentioned orbital diversity, that's one. But we want to make sure that we also add new capabilities as they see fit. Out of the NOAA study, one of the most important measurements that was highly valued was measuring three-dimensional winds throughout the depth of the atmosphere, all the way down to the surface, including ocean surface vector winds. And we also want to make sure that we maintain continuity of measurements by one means or another of the products that are produced by JPSS right now. We might do this in a different way than we did in the past. More small satellites launched in different orbits on a regular basis, looking to the commercial industry to provide data, to provide ride shares or other types of instruments that could help us out, and just developing new instruments as well that we could fly on our own satellites or with our partners, or again, partnering with industry might be a way to do that. So here's an example of a success story. This is Cosmic 2. These are for global navigation satellite systems, radio occultation, basically taking soundings of the atmosphere by looking through the atmosphere at GPS or other GNSS satellites. These satellites are fairly small compared to JPSS or GOES-R or other NOAA big satellites, coming in at about 300 kilograms. And they're only about a meter and a half cubed, so they're really not that big compared to the nearly minivan sized other satellites that we fly. These particular ones are flying in a equatorial orbit, about 24 degrees inclination, at about 520 kilometers, and they're producing on the order of about 4,000 high quality profiles per day. And out of NOAA, we thought that about 5,000 from government sources would actually be quite valuable, and we would buy our way up from there with the assumption that industry would be able to provide quality soundings as well. So let's take a look at instrument capabilities that we might have. On the right, you see a figure of JPSS satellite with the Advanced Technology Microwave Sounder circled in yellow. It's a fairly big instrument, very capable microwave sounding instrument, but it's about 85 kilograms, and it's cost over $120 million for each copy, or at least that was the price for JPSS-2. On the left, you see a notional microwave sounder that comes in at maybe 5 kilograms and costs maybe $10 million. And these are the type of changes that we're seeing in instruments and in flight and in just the size of buses and so on. Now, granted, these two sounders may not be of the same capability, but if we fly more of the smaller ones, does that make up for the bigger ones? And we're looking into that right now. So last year we began what would hope to be an ongoing engagement with industry. We released a broad agency announcement last fall that was looking at mission and instrument concepts both in the geo and extended orbits regime or in the low Earth orbit regime. And what we were looking at was instruments, constellation concepts, mission concepts of a variety of different ways. Are there ways to make instruments smaller, equally capable, or even more capable? Where are the knee and the curves with respect to instrument capability versus cost? We're looking at other types of business models, data buys, data ride shares, data as a service from industry. We're looking for partnerships. We're looking for a number of different ways that we could implement our regional real-time imagery, the stuff that you get currently from GOES 16 and GOES 17 now, potentially in different ways. Is that feasible? Is that something we even want to consider? So we got a number of different white papers back, and we selected 14 each as of early July from the GEO side and from the LEO side. And on the GEO side, 2 of those were actually implementing the GEO type of measurements, the regional real-time measurements of imagery from LEO platforms. And that's actually a very interesting study that we're looking at right now. So what do we do with these studies once we're done? We want to make sure that They support our new methodology, our new way of thinking here in NOAA to come up with agile, mission-effective, and cost-effective missions. We want to make sure that they support high update rates beyond what we provide today. And we also want to look forward to possible demonstration missions where we would say fly before you buy, to see if it's the type of capability that we want, the type of capability that we need, and is it cost effective, and is the technology really there? So let's take a look at some of the contracts that we offered. I broke these up into 3 different categories of instruments, missions, and constellations, although these are really arbitrary categories and some of them do cross over. So you can see that we had a broad range of different companies, some large, some small. Some companies got together with each other in order to write proposals. But a number of them were focusing on instruments because we asked for that, and these were instrument companies that responded. Others were bus-type companies responding with how they would implement a particular mission with their buses and getting instruments from other people. And then others provided us with full-blown constellation concepts, basically soup to nuts, how they would do the entire mission, how they would provide the data to us, and different ways of how we would go about paying things like that, for things like that. So very, very interesting, very, very diverse set of viewpoints, and we were going to use all the things that we learned from these studies to inform how we move forward. And one of the things that we're thinking about on how we move forward is to change our launch cadence. As I mentioned before, we currently launch somewhat irregularly and pretty far apart between when JPSS-1 launches and when JPSS-2 launches, and when even the predecessor satellite to JPSS-1, SNPP, launched. So what we're proposing is to come up with a launch cadence on a 2 or 3 year basis. So the idea behind this, we're calling this the train leaving the station, is that we will be scheduled for launches on a 2 year or 3 year cadence, and whatever instruments are ready, whether they're demonstration instruments, whether they're actually flight model instruments to fill out our constellations, or they're really novel type of different type of measurements that we haven't done in the past, they will fly if they are ready to fly. If they're not, they miss the train, we wait for the next train to come in, but the idea is to have a constant level of funding if we can achieve that, if Congress will support that, in order to make this a reality. And that way, we'll be constantly launching, constantly injecting new technology into our constellations, constantly reviewing and filling out the constellation designs that we have in order to provide our customers with the best data possible, the greatest amount of data possible for them to use when they need it and where they need it. So the next step in the emerging LEO paradigm is the BAA. Well, the BAA was the first step. After this BAA, we plan on likely issuing another one in the fall, or possibly RFPs, where on the LEO side, we're looking to enter into Phase A in 2022. So we have another year of these instrument studies and constellation studies that are going to be a little bit more in depth. And the first one that we're doing right now is based on sounder technology. So we're calling it SounderSat, and that's the first one that we want to launch in the mid-20s as a demonstration mission with full implementation in the early 2030s. But beyond that, we have a number of other technologies, or a number of other requirements that we have that we want to fulfill. I'd mentioned 3D winds earlier, and again, these include ocean surface vector winds all the way down to the surface. But we're also interested in things like low light imagery, global precipitation, regional real-time imagery, and a whole suite of other measurements that we currently make that we might be able to do in a better way. We want to make sure that we maintain our ongoing dialogue and partnership with the community, and that community includes industry as well. So a possible constellation might look something like this, at least on the LEO side, where we have our partners there. Obviously not showing if we have a full constellation of LEO that is fully disaggregated, but we want to make sure that our architecture consists of smaller satellites that are more agile, where we can inject new technologies quickly and be able to provide the information that we need in real time to the user community. Starting off with sounders, since they're so important to NWP, and then moving forward to some of the other measurements that I'd mentioned. So thank you for your support, or your you're watching this video. And if you have any questions, please feel free to ask us in OSAT. Thank you.